welcome to the video tutorial for 5.1.1. This time, this is part 2. So there's the video for part 1 already up. And this time we're focusing mostly on electric fields. So our learning objectives for today is to describe and sketch the electric field lines around a single charge and around adjacent charges or two adjacent charges, and to define electric field strength. Okay, so first off, we want to define and sketch the electric field lines around a single charge. This is pretty straightforward, but first let's maybe define what an electric field is. So an electric field is quite similar to imagine in relation to our gravitational field. So gravitational field exerts a force on masses, on each other actually. So it's an attractive force. Both masses are pulling towards each other. And usually it's at this point that somebody might say, well, why don't we pull the Earth towards us? And that mostly has to do with Newton's first law of inertia. Because the Earth is so big, and we're just a tiny little speck, probably even smaller than that, the gravitational pull that we exert on the Earth really isn't all that much. And so we tend to get pulled towards the Earth rather than the other way around. But the force of gravity is actually exerted on both objects, just that the Earth doesn't move very much. Okay, a little bit off track there. An electric field is a field vector or a vector field that associates 2-point charges in space. So remember, a point charge is the textbook likes to say an infinitesimal point charge. And really all that means is that it's very, very small, a speck, okay? So a tiny little thing, one single point, okay, is what we're talking about. And I feel point charge already does that, so I leave the word infinitesimal out. Infinitesimal. Okay, so textbook likes to use that, but just imagine it is extremely or really, really small. Okay, and exerts the electric force. So let's maybe look at some examples on our electric field in terms of the lines. All right, so first up, we have a positive charge. And notice that the positive charge, all the arrows point away from the positive charge. And I would encourage you to maybe take a moment and guess and just imagine which way the arrows might point on the negative charge. So take a moment, just have a little think about that, make a hypothesis. Okay, so hopefully you've had a moment to think about that. If positive is going away, then negative charges, remember, are opposite to that. So they're going to be pulled towards the negative charge or the electron. So they look like that, exactly opposite of each other, as you may have expected. Okay, so below we have, so this is looking at it from an individual perspective. Let's look at how they interact with each other. So we have a proton or a positive charge and an electron or a negative charge. And we know that opposite charges attract. So we are expecting an attraction here. So if you think about what happened before, it sort of forms a line here now, doesn't that? Okay, so that's actually exactly what these lines are doing. Okay, so positive to negative, and this is just sort of indicating it's going so far out that we don't see it. So really, like, this line should have connected over here, this line should have connected over here, but of course this is just making my diagram really messy, but that's what it's meant to mean. Okay, so sorry, I'm just going to temporarily connect it while I draw this arrow here, right? So it's actually going through that. Whoops, erase too much. Okay, and then again, this guy over here is actually connected all the way there. Well, I suppose it's like more or less like that. Okay, and then so yeah, it's going to do something like that. Okay, so just clearing that up. And likewise, it's sort of the same idea for here. It's just it's so large that we can't actually see the whole thing. And this is perfectly okay to draw the diagram like that as well. Okay, so usually I draw two arrows, one pointing out. You can draw more than two. And the idea is that, oops, I messed this up, didn't I? I messed these guys up. Okay, these guys are supposed to point away. Okay, so pointing away, everything's pointing away from the positive and into the negative. All right, this is attraction. 2-point charges of opposite charges. So let's look at what happens when they're exactly the same. So remember our positive charges. This is going to repel an object. So interestingly enough, I'm just going to highlight this. Actually, let me just draw the arrows first. So remember, everything points away from the positive charge. So just something like that. Okay, I'm just going to draw one arrow on everything. So away, away, away. Whoops, reverse that one. Away, all pointing away. Okay, and of course you can draw more than one arrow if you like. So I'm just trying to do this as fast as possible. And so we're going to be left with, now I just want to quickly talk a little bit about what would happen if we had a point charge. Okay, so I'm just going to use red to demonstrate that it's a positive charge, but it's a point charge, so it's very tiny in comparison. Okay, so this little guy right here, that little guy in the center, is actually in a nice state of equilibrium. Okay, it's if the two charges on the left, the positive charges on the left and right hand side. So suppose this is a 1.6 times 10 to the negative 9 coulombs, and this is 1.6 times 10 to the negative 9 coulombs. Then that charge would actually be in equilibrium right in the middle. Okay, and then if it were a little bit further away, so suppose it's now up here, then it would get pushed away by both of the charges. So let me just maybe label these 2 points, okay? So point B, it would actually get pushed upward. And then suppose if it was down here in point C, it would get pushed downwards, okay? So that's what's going on in terms of having two positive charges. Now let's look at the exact opposite of that, which is to have two negative charges. Okay, so again, let's quickly get some arrows in here. So remember, negatives points towards itself, right? So if we look back at this diagram, right here, it points towards itself. And so that's what we're going to do. So pointing towards into the negative charge. And I'm just going to keep going as fast as I can. And then we have this also pulling things, a positive charge inwards. So everything, all these arrows is always drawn in relation to how a positive charge would work. Okay, so that's why sorry, I should have mentioned that a little bit earlier, but every single, the direction, well, it's actually mentioned down there, but so I'll save that for a little bit later. So that's why the arrows are the way they are. It's in reference to a positive charge. So again, if we had a tiny little positive charge at A, it would be pulled this way and this way. And again, assuming that both negative charges are the same, then again, it's a nice state of equilibrium, okay? If it was over up here in B, it would get pulled down, and it might actually even oscillate back and forth. It would, if it was exactly in between the two, it would actually oscillate back and forth a little bit. And then eventually, if it was frictionless, actually, it would actually oscillate back and forth permanently. But if there was some amount of friction, then it would eventually reach point A as an equilibrium point. So that's, again, some really interesting physics. You would actually almost combine simple harmonic motion with the electrostatic unit. Okay, other points like point C. Okay, so point C would actually, it would experience some force this way, okay, but mostly it gets directed this way. And we'll see this a little bit later, is that once it reaches points, field lines of higher density, then it increases in magnitude, okay? So eventually it would get sucked down into this negative charge over here. Okay, so some of the things that I probably should have mentioned earlier, but I've got it written here right now, is that electric field lines have the following properties, okay? All the arrows that we saw is in reference to point charges, and it points away from the positive into the negative, okay? So it's that, it's a positive reference point. Okay, so that's really, really crucial to remember that. Field lines will never cross each other. Thirdly, field direction is a tangent to the lines. And areas of high density, we just mentioned this, has a stronger field, and low density has a weaker field. So if we look at some of these photos below here, so I just tried to do a sort of a cutout or a cross section here where this has high density. So it's going to experience, this is going to magnify the electrostatic force, okay? This is low density. So it's going to be a lower electrostatic force. And this is our last little bit here, right here. We're talking about parallel lines. So where they're parallel, then the field is uniform. And we're going to see a little bit more about this later when we look at electric plates. So this is a uniform field. Okay. So on to our second learning objective, to define the electric field strength. So this is mostly a formula, and the definition of the formula is that the electric field strength is the magnitude of the force per unit charge, on a positive charge. So again, everything is in relation to a positive charge, or how a positive charge interacts with a field. And so here we have E, we have F, and then we have Q, or little q we like to use, because it represents a point charge. So it's really, the charge is very small, but we know it's positive, okay? And so very quickly, the units is, electric field doesn't have its own unit. It's newtons per coulomb. So that's just coming from the other two guys, right? Charge is in coulombs, measured in coulombs. Force is measured in newtons. So newtons per coulomb is the electric charge, or that's how the textbook likes to write it. Okay, so our first example here, sorry, I'm kind of spoiling this a little bit for you guys already. I probably should have cleared this out already. So first thing I want to highlight is that we're going to be rearranging or combining two different formulas. We're combining Coulomb's law, and we're combining our electric field formula. And what we're going to do is that, notice in Coulomb's law always talks about two charges. And we use, they like to use big Q for larger charges, and they like to use little q for point charges. But if you remember last time, both of these Q1 and Q2 can represent point charges anyways. And so it just arbitrarily represents, I mean, sometimes in some textbooks, they write it as little q1 and q2. And that's perfectly fine as well. Okay, it's just that they represent two different charges. But sometimes we also have an alternative notation, as I mentioned over here, where we have big Q and little q, okay? But we can, as long as they're two different charges, that's all Coulomb's law really cares about. So what we're going to do is just to help our brains understand a little bit of this, we're going to let Q1, so sort of I kind of change things up a little bit. We're going to let Q1, so either little q or big Q, doesn't really matter. Q1 is going to represent the proton from our question. So proton has a charge of 1.6 times 10 to the negative 19. Then we're going to calculate the electric field at a distance of 2.5 meters. So originally it kind of seems like, it kind of has something to do with Coulomb's law, but then we're also talking about electric field. So what's going on? So we're actually going to do a little bit of rearrangement. So I kind of spoiled it a little bit earlier already is I'm going to isolate force on one side. And remember, this is the electric force, which is the same as the force in Coulomb's law, which means we can actually take this guy and we can substitute it onto the other side of that, which is exactly what we're going to do right now. So we're going to do F, sorry, not F, we're going to do E. F is substituting, EQ is substituting into F, and you have K, Q1, Q2 over R squared, okay? So a quick little just notation there is that I'm going to let Q1 represent the proton and just little q to represent the point charge, okay? So what that allows us to do then is that we don't even need to know what the point charge is, because you can see that it wasn't given in the question, but that's because they cancel out here, okay? And so we sort of have a new formula, which is E KQ1 over R squared. Okay, and then we're going to make our substitution. K is Coulomb's constant, so that's 8.99, sorry, 9.9, 9 times 10, 9 times 10 to the power of 9. And then we're going to have our proton charge, 1.6 times 10 to the negative 19 coulombs. I'm just going to skip the units for now. And then our distance of 2.5 times 10 to the negative 15 meters. Okay, so we're just going to do negative 15, negative 1.5 there. And then when we complete our calculations, I've got it completed here already, is that it's 2.3 times 10 to the power of 20 newtons per coulomb. So that's the answer right there. Okay, so the important part is understanding or learning about that we can combine both the electric field equation and Coulomb's law. And so if we look at this, we can actually backwards calculate what the electric force would have been. Okay, so now that we have the electric field, we can just do a straight substitution. E equals to F over Q. And if we want to find the force, so again, I'm just going to rearrange that, E times Q. And so, oh, wait a minute. I can't do that, can I? I don't know what the little charge is. Sorry, no, the first, it's the same charge. So determine the force exerted on another proton. So we're talking about the charge of a proton this time, not the mysterious point charge. So this makes life a little bit easier then. So F equals to E, 2.3 times 10 to the power of 20. And then now I forgot to mention this as well. The charge of a proton is given to you in your data booklet. So it's not something you have to memorize, but eventually when you do enough work, you will memorize it, or it'll kind of stick in your brain. So you don't have to forcefully memorize it, but when you write it down enough, you'll remember that, okay? So I did a little bit of pre-calculation there already. This is actually example number 4 from Cognity. So this is example number 4 from Cognity, if you want to check back in the textbook, okay? So we've done that together already. Here's another example that is kind of similar to another one that's in the textbook. I don't want to spoil that one for you, so I just did a slight little variation of it. So suppose there's a black hole. So there's a black hole, very far away. So it's far enough that it's not dangerous, but far enough that it has a gravitational pull. Okay, so we know the black hole is going to pull things in, but for now, the gravitational field here is very weak. But it is going to pull this proton towards the black hole. So if a proton and electron have exactly the same charge, and they do, in terms of opposing charges, so where should we place the proton? So this hopefully should be pretty obvious, is that we have to place the electron on this side. And remember that our field lines go like this, right? It points away from the proton towards the electron. Okay, remember everything is in reference to what a positive charge would do. Okay, so positive charge would be repelled away from the proton and attracted towards the electron. Okay, so what we're also doing here in this question is I'm introducing the idea that two different forces, the force of gravity can be, in this particular case, equal to the electrostatic force or the electric force to create an equilibrium. Okay, so if the magnitude of this, let's say it was, 2 times 10 to the power of negative 30 or something like that, and this is also 2 times 10 to the power of negative 30. If this was completely parallel, right? If they're on the same line, then yeah, this would work and keep the proton in equilibrium. Now that's assuming that this guy is able to withstand the pull of gravity. So we're sort of assuming that this guy is not affected by gravity. So we're kind of making up the situation, or that it's somehow able to stay away. Okay. So main idea here is that the two forces, electric and gravity, can work together or against each other to create either an equilibrium situation or even a situation where it speeds up the pull of an object. Okay, guys, thank you for watching. I'll have some questions assigned from the textbook for you guys. See you next time for 5.1.2.